Yes, so my lab is at the University of Montreal in the Department of Chemistry. And we use mass spectrometry to query the molecular composition of tissues in particular. Imaging mass spectrometry, which is the technology I developed, aims at mapping the molecular content of an area. And then we apply this to the study of biological material. And we do this on a flat material, so we generate tissues from biological material, tissue sections, which are mounted on flat surfaces, and then these allow us to probe these sections, pixel by pixel, if you will, coordinate by coordinate, and at each coordinate we record a mass spectrum with molecular information, and based on the intensity of a signal, we can map the intensity across the section and see where it does express and where it's not expressing, and so on. So there's several aspects to this technology. There's a lot of fundamentals that go into the technology. That is instrumentation, sample preparation, data analysis, and it's impossible these days for a single lab to address all of these at once. What I like to do the best is sample preparation. And for the past 15 years, my lab has been focusing on methodologies and protocols to improve specificity and sensitivity of the methodology. When you do a liquid chromatography tandem mass spectrometry experiment, you have up front the liquid chromatography that'll separate things out, ideally allowing molecules to arrive one at a time at the mass spectrometer to be detected efficiently. We don't have that luxury with MALDI mass spectrometry, which is the technology I use, where all the ions are desorbed at once and analyzed at once, right? So that creates a situation where detection efficiency is not ideal because you're trying to detect everything at once. Not everything ionizes in the same way. And so there's some biases in what you measure. So how can you improve on that? One way to do this is to prioritize sample preparation to preferably detect certain classes of biomolecules up to the point where you want to detect a single type of biomolecule. And there's a lot of leeway here on how to do that. One approach is to do what's called on-target chemical derivatization, where you know your target has a certain chemistry, has a certain reactive group, and you're going to bring in a molecule which will specifically react with these reactive groups, right? And allow you to what's called desorb and ionize. Chemical derivatization is one approach. The other approach I'm working on is to functionalize the surface on which we deposit the tissue section, right? So you can chemically modify this surface to actually privilege the reception or the capture of molecules that are interesting to you in the tissue section. So you modified your surface, you put the section on top, you allow transfer of these molecules of interest, you remove the section, and then you measure the imprint.
You're right there.
Right? So there again, you augment the specificity of what you're looking at because you preferably capture what you want to look at. And then because there's less molecule captured, you also improve sensitivity. So it's these systems I like to play with and I like to develop.